thank you to Brilliant for supporting PBS. Physics is this close to understanding the entire universe. But what lives in this gap? Many physicists think that it's the elusive graviton, the quantum particle of gravity, whose discovery will finally allow us to stitch together our two great theories of nature into a single master theory. But what is the graviton, and does it even exist? We have a couple of important announcements before we get started. First of all, it's time for the PBS Annual Survey. We're looking for your feedback. Every year, PBS conducts an audience survey to gauge our audience's interests, vote on show ideas, and help shape the future of PBS. We really do look closely at the data, and it's incredibly helpful. Also, the Spacetime fans have been one of the most well-represented fandoms on the survey, and we'd like to keep it that way. We put the link in the description, and if you have a couple of minutes, we'd love to hear from you. Next up, we're still battling the algorithm, and by liking and commenting on the episode, you help get the episode shared with more members of the Spacetime community. It really does help. You can also subscribe and hit the bell icon to get notifications. Lastly, if you want to believe in a future with warp drives, you can head over to the merch store to get an I Wanna Believe UV Glow t-shirt or sweatshirt. The quantum revolution started when we realized that light is made of particles, photons. Max Planck guessed it and Albert Einstein proved it. Light is a wave in the electromagnetic field, so even from the beginning of modern physics, we have this idea that a force, the electromagnetic force, is communicated by these particles. As quantum mechanics evolved into quantum field theory, we also found the particles for the weak and the strong forces. That's 3 out of the 4 fundamental forces, leaving only gravity lacking a mediating particle. So if we could just figure out the graviton, we'd have united all of the forces of nature and be on track to a theory of everything. We are now 100 years after the birth of quantum mechanics, and much of the past century of work towards the master theory hinges on the existence of the graviton. But does it exist? If not, much of the work in unifying these theories has been in the wrong direction. Now, we can describe the entire universe in terms of quantum mechanics and general relativity, yet they look wildly different to each other. On the quantum side, we have these fields filling all of space, whose oscillations give us the known particles of matter and 3 of the 4 fundamental forces. These quantum fields fracture into discrete shards as we zoom in, and their properties and their particles can never be pinned down precisely. But on the relativity side, we have space and time merging into a unified fabric of spacetime, a fabric that can expand and warp. It stretches in response to matter and energy, leading to what we experience as the force of gravity. It's a pretty effective picture. Quantum theory gives us the stuff of the universe, relativity gives us the container. Matter in spacetime. Matter tells spacetime how to curve, and spacetime tells matter how to move. So if this picture works so well in describing the universe, why do we need to try to force gravity to work the same way as the quantum forces? Well, partially because the two theories are so different. We expect, or at least hope, that all of the complexity that we observe in the universe emerges from unified underlying laws. That proved to be true of all of matter and most of the forces of nature, quantum fields all the way down. It would be weird if the most fundamental layer of reality was actually 2 unrelated things, and extra weird if the theories describing those things are profoundly different, as they are in the case of quantum mechanics and general relativity. The former is fundamentally discrete and random, but the latter is fundamentally continuous and deterministic. But maybe that's just how it is, 2 separate theories. It's not very elegant, but does the universe care what we find pretty? Now there's another reason, besides aesthetics, that we need quantum theory and relativity theory to connect. It's because at a fundamental level they actively contradict each other. Together they describe most of the universe, but in certain places like the center of a black hole or at the instant of the Big Bang, they generate contradictions and paradoxes that it seems, can only be solved by finding the master theory in which quantum mechanics and general relativity connect seamlessly. For various reasons, most physicists trying to solve this problem follow a particular path, the path of particles. They try to quantize gravity, just as they once managed to quantize electromagnetism. And the search for this theory of quantum gravity implies a particle that mediates gravity. That's the graviton. If the graviton exists, then gravity has to be quantum, and vice versa. Let's see why that's the case. So to get a photon, we start with the classical electromagnetic field, the one described by Maxwell's equations. A field in this sense is just something that extends through space and has some value at each point in space. That value can be a simple number, like say the density or temperature of the air in the room, giving us a density or temperature field. Or it can be a vector, a number and a direction. The EM field is like that, a strength of the force and a direction at every point in space. Fields can support waves, oscillations in the field strength that move through space. The density field in air supports sound waves. The EM field supports EM waves, which we know of as light. So when Planck and Einstein showed that light is made of indivisible particles, we were set on the path to quantizing the EM field itself. This process of quantization followed the development of quantum mechanics in the mid-20s and quantum field theory in the following couple of decades. Through quantization, the EM field is broken down into countless modes of all different frequencies. In this new description, even the empty or vacuum state of the EM field is made of those modes, made of infinite electromagnetic waves stacked and cancelling into nothing. And those virtual modes are made of discrete packets, just as is the real EM wave made of photons. So we can say that the EM field is made of virtual photons. In quantum field theory, we describe the quantum electromagnetic force in terms of other charged particles exchanging these virtual photons. Those photons take momentum from one particle and give it to another, causing the push and the pull that we see as a smooth electromagnetic force. Photons mediate electromagnetism. And we've talked about whether these virtual photons can be thought of as real before, but what is real is the fact that the EM field is extremely well described as being made up of quantized chunks. If we use basically the same process to quantize slightly more complicated fields, we get other quantum forces and their mediating particles, the gluons of the strong force and the W and Z bosons for the weak. It should not be taken lightly that this stuff works so incredibly well. We take a classical field, make some symmetry arguments to guess what other fields might exist, apply quantization rules, and boom, we figure out almost all of the particles and forces that make up our universe. The standard model of particle physics is arguably the most successful theory in physics and perhaps in science. It's not surprising that we'd want to envelop gravity and space-time into the explanatory magnificence of quantum field theory. So, how do we proceed? Well, we need to identify the field that we are trying to quantize and then apply the quantization rules just like we did with the other forces and fields. We do know that gravity behaves like electromagnetism in some important ways. It has a strength at all points in space. It also supports waves, gravitational waves, that also travel at the speed of light. There are differences, however. According to general relativity, the gravitational field is not a field on top of space-time like electromagnetism, but rather, in a very real sense, it is the fabric of space-time. This tangling of what the field is and what it lives in is going to be a problem, as we'll see. But for now, let's proceed. Let's get a little more precise. In the Einstein field equations, the field we're interested in is encapsulated in something called the metric tensor, a 10-valued object made up of scalars and vectors with the value of every point in space. It's a field, albeit a very complicated one. Now, where the EM field can be thought of as a thing living on top of the background grid of spacetime, this tensor field of GR in a real sense, is the grid of spacetime. In electromagnetism, the field changes with respect to the grid. In general relativity, the grid itself changes. This is going to prove to be complicated. But nonetheless, the grid, this spacetime, this tensor field is the thing that we need to quantize, so let's do that. We'll start with an approach that hopefully won't break anything. We're going to treat the gravitational field as a small fluctuation, a perturbation, to an imaginary flat and static background. We poke the flat spacetime very lightly and see what comes out, hopefully a graviton. This is a very standard approach in physics. It's called perturbation theory. Rather than completely changing our model, we just make a tiny adjustment to what we already understand and we see what happens. The result is usually a good approximation to reality, assuming the perturbation is very small. Take, for example, electromagnetism. We can understand the quantum behavior of this field by taking account of the exchange of different nudges to the electromagnetic field as represented by the exchange of virtual photons in different ways. For a weak electromagnetic interaction, only the most obvious exchanges matter, like the exchange of a single virtual photon. Stronger interactions require us to account for more complex exchanges, but it all works out beautifully and gives us the incredibly powerful quantum electrodynamics. When we do this to the gravitational field, everything is also fine. Not only can we do a sort of gentle quantization of a weak gravitational field, we get a glimpse of the quantum of that field, the quantum that mediates the gravitational force. The graviton, well, what does it look like? Well, it inherits all of its properties in a pretty non-negotiable way from the field it comes from. It's a massless spin 2 boson. Massless means it travels at the speed of light. Spin 2 just means it has a 180-degree rotational symmetry that reflects a sort of stretch-squish action on space, just like the gravitational waves that should be made from these gravitons. And boson just means you can stack infinite gravitons together to make, for example, gravitational waves. And just as virtual photons make up the quantum EM field, we can build the fabric of spacetime out of virtual gravitons. Cool. In a sense, we just succeeded in quantizing gravity. This approach of perturbative quantum gravity actually kind of works. We can use it to recover classical gravity, and we can even use it to make predictions, like Stephen Hawking's prediction of Hawking radiation, leaky black holes. So why don't we just stitch this type of quantum gravity to the rest of quantum field theory and say we have a theory of everything? Why not just add the graviton to the standard model library and move on with our lives? Not so fast. We need our final theory to explain the whole universe, but our perturbative quantum gravity only works in the case of very weak gravity. It doesn't work for places with extreme spacetime curvature like the centers of black holes. We also want to actually verify our quantum gravity theory with experiment, and our perturbative theory only works in situations where it's essentially impossible to differentiate it from regular Einsteinian gravity, at least with a human buildable experiment. We really need a full theory. So to finish the job of quantizing gravity, we have to see if we can generalize this to a theory that works everywhere, including where gravity is extreme. Now, as gravity gets stronger, our perturbations get bigger, and the corrections we need to make to our classical theory get larger. More technically, we need higher order corrections represented by more complex interactions via virtual gravitons. So remember how we do this for quantum electromagnetic interactions. We calculate the quantum EM force by summing over the possible virtual interactions that could have potentially occurred. For weak EM fields, it's enough to include only the most probable of such interactions, and that means the simplest ones, like the exchange of a virtual photon or two. For stronger EM fields, more complex interactions become important. That includes so-called self-energy terms, which result from the feedback between the different fields. These higher order terms involve loops that appear in the many Feynman diagrams that we sum together to compute a strong interaction. In a previous episode, we talked about the connection between these loops and the measured mass of the electron, and how they appear to make that mass infinite. But these sorts of infinities can't be real, or we wouldn't have a universe. So in regular quantum field theory, we have a way to remove them. It's called renormalization. It lets us sort of divide out the infinities by grounding them in measured values, for example by measuring the true mass of the electron. This is possible with regular quantum fields because the perturbative expansion, the sum of Feynman diagrams, only generates a finite number of infinities. That means it's still possible to absorb these into a finite number of additional terms added to our equation. Even if absorbing infinities sounds a bit hokey, it works incredibly well by grounding our otherwise infinite predictions in a few finite measurements of the real universe. Quantum field theory is able to make stunningly precise predictions of many things. Not a bad trade-off. Depicting the EM field as being made of virtual photons is successful, and that forces us to take seriously this picture of a quantized EM field. At some level, we believe that the EM field and the other quantum forces are mediated by particles. If we can do the same thing for gravity that we did for electromagnetism, then we can make the same argument for the reality of the graviton. So, we're ramping up the strength of our quantum gravity, increasing the complexity of our perturbative expansion, and hoping we can renormalize any infinities to get a sensible theory. And this is where everything goes catastrophically wrong. The problem is that gravitons interact gravitationally. They interact with themselves. The photon, on the other hand, does not interact electromagnetically, at least not directly. It interacts with, say, the electron field, which feeds back on the EM field. That extra step limits the complexity of the photon self-interaction and limits the number of self-energy loops, making renormalization possible. But a graviton can directly spawn other virtual gravitons, which can spawn more virtual gravitons ad infinitum. Instead of a finite number of self-energy loops, we get an infinite number of terms in our perturbative approximation that can't be renormalized or cancelled out with a finite number of real measurements. In cases of strong gravity, our quantum gravity theory becomes meaningless. We say that perturbative quantum gravity is non-renormalizable. We can also think about this in terms of the strength of the gravitational coupling. The gravitational constant gets stronger as the field gets stronger, ultimately sending the field's strength to infinity. So, this straightforward approach of quantizing gravity leads to nonsense. Maybe then it follows that we can't build the gravitational field out of gravitons after all. And does that mean that the graviton doesn't exist? Well, not really. What it means is that this simple picture of quantum gravity that we get by applying the same quantization methods as the other forces isn't right. There may be a theory of quantum gravity that just can't be got by the simple perturbative approach. Interestingly though, the graviton itself that we found by that method that apparently doesn't work may lead us to the final answer. So even though the perturbative approach didn't get us all the way, that picture of the graviton is almost certainly right. If the graviton exists at all, then it has to be a massless spin-2 boson. Nothing else can generate the Einstein field equations in the classical limit. And that's why when we find a theory that predicts a massless spin-2 boson, our ears prick up and we wonder if we found a potential for quantum gravity. And that's exactly what happened with string theory. This was originally meant to be a theory for quark interactions, but a graviton-like particle popped out of the math in such a profound way that it sparked a many-decade quest to find a stringy theory of everything. You can't avoid the graviton in string theory, and in string theory, you also avoid the rampant infinities, because at the smaller scales where gravity can be the strongest, the graviton field itself is smeared out over the vibrating strings at the theory's core. Now, there are other approaches to quantum gravity like loop quantum gravity and others. All of them have a graviton because without a graviton there's no path to classical gravity. It's again sounding like the graviton is inevitable, but again, no. It's only inevitable if gravity is fundamentally quantum in the first place. If the final theory looks more like quantum mechanics than general relativity, then we need a graviton. But what's the alternative? Well, it's that the fabric of spacetime doesn't have discrete chunks. It's not made of gravitons. Maybe a smooth, continuous spacetime is fundamental in some way. Now, a number of theories favour this option. Even Roger Penrose is a proponent, encouraging us to gravitize the quantum rather than quantizing gravity. Fit quantum mechanics into general relativity rather than the other way around. Ultimately though, finding evidence of the actual existence of the graviton will be critical to confirming the quantum nature of gravity and even which quantum gravity our universe has. Now, as I hinted, that's going to be really hard to do directly. We'd need to build a solar system-sized particle accelerator. Fortunately, there are brilliant methods to observe the indirect effects of the interactions of a quantum graviton that we can do right now. For example, spotting the mediation of quantum entanglement by a gravitational field or a Cavendish experiment, but with exceptionally tiny masses. One of these methods may pan out very soon, or we may have to start astro-engineering our mega collider. Nature has set a last gigantic hurdle to understanding her deepest laws. We need to understand and then to find the graviton, and then we'll hold the building blocks of spacetime. Thank you to Brilliant for supporting PBS. Brilliant is where you learn by doing, with thousands of interactive lessons in physics, math, programming and AI. Brilliant helps you build your critical thinking skills through problem solving, not memorizing. Each lesson starts by helping you master the foundations, then levels you up to increasingly challenging problems. And if you're into physics, Brilliant offers a calculus course designed to help you understand how physics works. In the calculus course, you'll begin with rates of change, explore derivatives, and work your way up to three-dimensional geometry. To try everything Brilliant has to offer, go to brilliant.org/spacetime or click the link in the description. Brilliant's also given our viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant.